Hi, this is Dr. Bricker here with some hints for homework number 8, which is over chapter 17. We are looking at light behaving like a wave in chapter 17. Now in chapter 18, which we just completed, we looked at light behaving like a ray, geometric optics. Depending on what light's interacting with, its wave characteristics might be exposed. So that's what chapter 17 is all about, and what homework 8 is all about. So in the very first problem, how long does it take light to travel through a 3.6 millimeter thick piece of window glass? So we know the speed of light in air or in a vacuum is about 3 times 10 to the 8th meters per second, but when light enters a medium, it actually slows down. So let's take a look at this one. So when light enters a substance, in this example glass, it actually slows down. So we know the speed of light in a vacuum is 3 times 10 to the 8th meters per second. But when we enter glass, the speed's going to be less. So if you take the speed of light in a vacuum, divide it by the index of refraction of the material that we're talking about. In this case, glass is 1.5. You can find that in the first section of chapter 17. You can figure out how fast light is traveling in glass. And then once you know how fast it's traveling, speed is equal to distance divided by time. They give you the distance in the problem. You can figure out how long it takes. So the amount of time it takes would be the distance divided by the speed. This is stuff from Physics 220, this part. The new part here is figuring out how fast light is actually traveling in glass. Alright, let's take a look at the next one. Okay, so a helium neon laser has a wavelength of 633 nanometers. It takes 1.33 nanoseconds, so 1.33 times 10 to the minus 9th seconds for light to travel through 33 centimeters of an unknown liquid. And we want to know what is the wavelength of light in the liquid. Okay, great. So not only does the speed change, so like at the last problem we went from 3 times 10 to the 8th to something less, the wavelength also has to change. Now the frequency will stay the same, but the speed and the wavelength will change. Let's see how this works out. Okay, so we saw this in the last problem that the speed changes, but the wavelength also has to change. So lambda is wavelength. The wavelength in a material is equal to the wavelength outside the material divided by the index of refraction. So the wavelength is going to be getting you're dividing it by a number over 1, so the wavelength in the material is going to be getting smaller. So the speed gets smaller, the wavelength has to get smaller. But again, the frequency stays the same. They're telling us the wavelength in a vacuum is 633 nanometers, so to the minus 9th meters. The amount of time it takes to go through a material that's 33 centimeters thick, the amount of time is 1.33 nanoseconds. So from this information, this is similar to what we did in the last problem, you could figure out the speed that you have in the material. So the speed in the material would be the distance divided by the time. So there's a couple of steps for this problem. The speed we have is this distance divided by this time. That's the speed in the material. Once you have the speed in the material, then you can find the index of refraction of the material, right? Because now you know the speed. The speed of light, you know, that's just a constant. So first use this to get the speed in the material. Then you could use this to get the index of refraction. And then finally, you could figure out the wavelength in the material. So you know the wavelength in a vacuum, given in the problem. From this step here, you can get the index of refraction. Then you can find the wavelength in the material. Okay, excellent. Let's look at the next one. Okay, the next problem is a double slit problem. So two narrow slits are 50 micrometers apart. They're illuminated with light of 620 nanometers. The light shines on a screen 1.2 meters away. What is the angle of the m is equal to 2 bright fringe measured in radians? And how far is this fringe from the center of the pattern? So you definitely have to keep in mind what this actually looks like. And remember, you could always hit this review button and this will take you to the exact correct chapter in the book. So it's a nice resource to have. So don't forget that that's always there. Now, with these double slit problems, there's not a lot of intuition built into this. So you really have to know what's going on. So it might help to hit this review section. Hopefully you've already read it, but now you're working on the problem. You want to a little refresher. Hit the review button here. Okay, so let's set this up. Okay, so here's the idea. Couple of slits here, so it's a double slit experiment. The separation between the slits, that's what little d is here. The distance from the slits to the screen is L. I'm using the same notation as the book. So when you shine light here, you get a interference pattern that looks like this. You've got a central maximum here. This is the brightest one, and then you get a fringe here, 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 here. These are all equally spaced apart. So m is equal to 0 just designates the central maximum, and then you have a spot here and here, you have a spot here and here, etc. The angle associated with the first fringe over here, I just called this theta m, that corresponds to m is equal to 1. There's another one here, this would be theta 2, theta 3, etc. So here's things we know. Slit separation, that's a little d. So you definitely have to keep track of this. You have to keep this picture in mind. You have to know what these things mean. And these are always in different units. This is sometimes in micrometers. The wavelength is in nanometers. The length to the screen might be in centimeters. So I just put everything into meters. So 50 micrometers for the slit separation. Wavelength 620 nanometers, so times 10 to the minus 9th. Now there's a couple of formulas that govern the behavior of double slits. So sine of theta is m times the wavelength times d. So m just designates again which one you're talking about. So this is 1 or this is 1, it's the same thing. It's symmetric. So in this problem we want to figure out theta 2. They're saying for the second bright fringe. So really this is just in general. The one that I'm looking at is actually this one. This is theta 2 that corresponds to m is equal to 2. So they give you this the fact that you're looking at the second fringe. So in this problem they're telling you m is equal to 2. So and we're trying to figure out the sine of theta. So you have 2, the wavelength is given, the slit separation is given. So you can use this formula to figure out theta 2. That's what they're asking for. How much is theta 2? Okay, so use that formula. Now, if you want it to come out in radians, have your calculator set in radian mode. If not, if you have it in degree mode, you can still do it in degree mode. This will come out in degrees. Then you'll have to convert it to radians. So that's the first part of that problem. The second part wants to know the distance from the central maximum. So it wants to know this from this central maximum over to here. Now the other formula that we have is just from a little bit of trig. So let me draw your attention to this first one I just have here. I call it theta m. Theta m, this distance is called ym, from the central maximum over to the middle of this fringe. Okay, so the tangent of theta m, is ym divided by the distance to the screen. That's just using a little bit of trig. So this is really the second formula that we have here. Okay, and that's just purely just based on the trig. Now there's something called the small angle approximation. When theta is not too big, the sine of theta is approximately equal to the tangent of theta. So if this is approximately equal to this, I can set them equal to each other. So when I set this equal to this, I get this formula. Okay, and you can use this to figure out, really we want this one, y2 will be equal to 2, that's the m part, wavelength, d, and then I've got to multiply both sides by L. So for this specific problem, this is what I could use. I mean, in general, this is true. But if I put in the fact that m is equal to 2, multiply both sides by L, I get this formula. So you can figure out the distance from the central bright spot over to this second fringe from this formula. Now, if you didn't want to use this approximation, although it works out really well because m is small, you could just use this formula. The tangent of theta, which now you know what theta is y sub m over L. So this would be y2 corresponding to theta 2. Okay, very good. Let's look at the next one. Okay, so this picture shows the fringes observed in a double slit interference experiment when the two slits are illuminated by white light. So white light just means we have all the different wavelengths of visible light all mixed together. When they go through the double slit experiment, they separate out by wavelength. So from the formula that you saw, the bigger the wavelength, the bigger the sine of theta is. So the more separated they are. So the bigger the wavelength, the more spread out the spot would be. So if you have blue light compared to red light, the light with the biggest wavelength is going to appear farther away from the central maximum. So that's the idea. Let's see what else we have here. So let's see, the central maximum is white because the colors overlap. This is not true for the other fringes. So m is equal to 1 clearly shows bands of color with red appearing farther from the center of the pattern. Okay? Great. So if the slits create this pattern are 20 micrometers apart, so that's little d in the formula, and are located 0.7 meters from the screen. Okay, so that was big L in the formula. What are the m is equal to 1 distances from the central maximum for red and for violet? Okay, so again, red wavelength is bigger than violet, so it's going to, the sine of theta from the formula is going to be bigger. So be careful here, they want the answer in centimeters. So it'll come out in meters, you'll have to change it to centimeters. So let's figure out the distance for red and the distance for violet and enter them separated by with a comma. All right, let's put this on paper. Okay, so here's what we just saw on the previous problem. I'm using the small angle approximation where the sine of theta is approximately equal to the tangent of theta. And you saw this on the previous page. Just keeping track of what these things mean is really important. So you'll have to refer to the picture that you saw. Actually, let me bring it back so you can see it. What does y sub m mean? Well, when y sub 1 means a different distance between the central maximum and the first bright spot, there's also one over here. Y is equal to 2 would be this one, like we did in that problem, this distance. So because we've got different wavelengths of light, they're going to have different distances from the central maximum. So the red wavelength is bigger, so the distance is going to be bigger from the central maximum. Okay, so keep that picture in mind. And then remember what these things are. Put everything in the same units. So slit separation, 20 micrometers, so 20 to the minus sixth. L is a distance to the screen, 0.75 meters. And we're talking about the m is equal to 1 bright spot. So the first one on either side of the central maximum. And we want to figure out y for red and y for violet. And I'm talking about the m is equal to 1 bright spots. Okay, so that's what this says. y1 for red, and then y1 for violet. Okay, so here's the formula that we have. A little bit of algebra. Y sub 1 would be equal to m, which is 1, times the wavelength. So wavelength times L divided by D. So I'm getting that from this formula. So multiply both sides by L. That's what this is, L, believe it or not. And put m is equal to 1, you get this formula. So for red, insert the wavelength for red. L is the same for both of them, that's just the distance to the screen, and D is the same for both of them. So here's how you actually would solve that. And then make a note that mastering wants the answer in centimeters. This will come out in meters. You'll have to turn it into convert it into centimeters. All right, let's look at the next one. Okay, so the next one A diffraction grating with 750 slits per millimeter is illuminated by light, which gives a first-order diffraction angle of 34 degrees. For steps and strategies involved in solving similar problems, take a look at the video tutor solution, get another perspective on solving these problems. So this is kind of similar to the double slit. It's just now we have a whole collection of slits. We get a similar pattern, but not exactly the same. It's the same idea, though. Light goes through several slits, interferes constructively and destructively. Because it's going through a small opening, the wave nature of light manifests itself. And as always, I keep saying this, but this is a great resource, this diffraction grating section of the book. So I just hit review, diffraction grating. This is a better picture than I could make. So this is from that section of the book. So diffraction gratings. Here is the kind of picture that you would get. So it's similar to what we have for two slits, but not exactly the same. We have a central maximum here, and then we've got spacing that looks like this. And these keep getting bigger and bigger. The physics part of this comes from this formula, that the sine of theta is m, and m just designates which one we're talking about, times the wavelength, times the spacing per slit. So, like, for example, if you have 1 millimeter per, and you've got a certain amount of slits, you'd have to figure out the spacing per slit, as it says down here, actually. Grating with n slits, or line, sometimes called lines, sometimes called slits, has a spacing of 1 millimeter per the amount of slits. Just be careful when you put the units in here. And then we also know, just from the trigonometry of the whole thing, we can figure out these different spots, like y sub m is L times the tangent of theta. Probably the way you think of this is tangent of theta is y divided by L. So these variables are similar to a double slit. The only difference is this is the spacing, the size per slit, instead of just the spacing in between any two slits like a double slit experiment. Okay, let's put this put some numbers to this problem. Okay, so here's what we have again, 34 degrees. We're trying to figure out the wavelength in nanometers, and they give you 750 slits per millimeter. So what is d then, little d in the formula? So the spacing is 1 millimeter for 750 slits. So that's 1 times 10 to the minus third meters for 750 slits, and then we can figure out the slit separation. So rarely do they actually tell you d. They just say a certain distance and a certain amount of slits, and then you have to figure that out. So be careful. It's the size divided by how many you have. So 1 to the minus third divided by 750. And a really small number here. 1, 2, 3, 4, 5, 6. 1.33 times 10 to the minus sixth, and then that's in meters, which again we want it to be in meters. Okay, so we got the angle for m is equal to 1. That's what they're telling you there. We're trying to figure out the wavelength, and now we know the slit size. So it looks like probably we could just go with this formula to figure out the wavelength. Right? We have theta, so we could take the sine of theta. We had to do a little bit of work to get d, but we have it. M is just equal to 1. So from this formula here, you can do a little bit of algebra, solve for the wavelength. Just remember, it's going to come out into meters, converted to nanometers. Okay, let's look at the next one. Okay, next one, a physics instructor wants to project a spectrum of visible light colors from 400 nanometers to 700 nanometers as part of a classroom demonstration. She shines a beam of white light through a diffraction grating. So white light has all different wavelengths. We could use this diffraction grating as sort of like a prism, because remember, the separation depends on what wavelength you have. So shining different wavelengths through here will separate the light from this central part based on the wavelength. The bigger the wavelength, just like the double slit problem we did. The bigger the wavelength, the farther it is from the center. So she shines a beam of white light. Diffraction grating has 600 lines per millimeter, projecting a pattern on a screen 2.4 meters behind the grating. Okay, so the distance from the diffraction grating to the screen is 2.4 meters. And we want to know how wide is the spectrum that corresponds to m is equal to 1, measured in meters, be careful. And then how much distance separates the end of the m is equal to 1 spectrum and the start of the m is equal to 2 spectrum. So by spectrum, they just mean all the different colors in between 400 nanometers and 700 nanometers. Okay, so we want to know, what is the distance to the 400 nanometer? Y. What is the distance to the 700 nanometer? And then we want to know the difference between those. So you have a distance to the 400, you'll have a distance to the 700. How wide is that? What is the distance between the 400 and the 700? And then the second part here, how much distance separates the end of the m is equal to 1? Okay, so the m is equal to 1 corresponds to whatever you figure out for the 700 nanometer color of light. And then the start of the m is equal to 2. So the start of the m is equal to 2 would be the m is equal to 2 band corresponding to 400 nanometers. Okay, so let's see what we can do with this one. Okay, so diffraction grating, again, you need to figure out what little d is. So it's 1 millimeter for 600 lines, so you have to do a little bit of work to get d. This is the distance to the screen, and we've got 400 nanometer wavelength light, 700 nanometer wavelength light. And we want to know, we want to take y1 of the 700 nanometer light minus y1 of the 400 nanometer light. That's what they're really asking here. You'll have a distance for the 700, you'll have a distance for the 400, subtract those. That's what they're asking for in part A. Okay, so how do you actually get these y's for the different wavelengths of light? So the only place that you see that appear is here in this formula, that the tangent of theta, this was purely from the trigonometry, is y over L. So y then is L times the tangent of theta. You know L, you don't know what theta is yet, but you can get theta from the physics part of it. So this describes the physics of it. Sine of theta 1, that comes from this formula here actually, sine of theta m is m lambda divided by d. So we want to get the, we're talking about the m is equal to 1 fringe, so sine of theta 1 would be m equal to 1 times the wavelength divided by d. So you can use this to get theta 1, and then once you have theta 1 you can figure out y1. Now there's two different wavelengths, so you'll have to do this for the 400 nanometer wavelength, figure out y1 for the 400, and then figure out y1, same procedure, for the 700, and then take the 700 minus the 400 to get the separation between these different wavelengths. So that's for the first part. The second part, they want to know the distance between y2 of the 400 nanometer and y1 of the 700 nanometer. So if you think about it, the end of the 700 nanometer first fringe, there's a distance. You'll get that from the first part. You've got to figure out the y is equal to 2 distance for that, the second spectrum, and that second spectrum begins with the 400 nanometer. So you already have this from the first part. You'll have to figure out y2 for the 400 nanometer and then subtract those. Okay, so same procedure to get this as we had for the first part. Okay, kind of maybe a little bit of work, but definitely doable for that one. All right, let's look at the next one. Okay, so the next problem is a thin film problem. So a very thin oil, index of refraction of the oil, so that's the film, is 1.25, floats on water, index of refraction of water is 1.33, and we want to figure out what is the thinnest film, but not zero, that produces a strong reflection of green light. And the wavelength of green light is given as 500 nanometers. Okay, so be careful of all these different units. So we want to know the thickness in nanometers. Okay, so let's take a look at this problem. So again, with many of these problems, you don't really have a whole bunch of intuition, so you really have to know what's going on and have that picture in your mind. So here's the idea. Here's up here is probably just air in this problem. I just called it N1 to leave it general. Here's film that is floating on top of something. So index of refraction of film floating on water in this problem. Okay, and the thickness of the film is T. So light comes in, some of it's reflected from this surface. Some of it is transmitted through the film and then is reflected at this surface. And here's your eye up here. So if these reflected rays arrive in phase, they add together and you actually see it. So by arriving in phase, I mean they're both the maximum when they hit your eye. They add together. And you actually see it. So this would be a case where you actually are seeing the ray being reflected. Now there might be a situation where you want to try, you don't want to see it, like you want to block out the glare from a road. So you might try to eliminate the light. So seeing it is called constructive interference. You actually see it. But maybe you want this ray and this ray to cancel each other out by the time it gets to your eye. That's called destructive interference. So it really depends on the indices of refraction of these three different interfaces. So in this problem, this is just air up here. This is the film. This is floating on water. So we've got to determine if we have any phase changes. So make sure you read through that section of the book. So remember, to have constructive interference, the path difference has to be a multiple of the wavelength for that to happen. So how do you determine if you've got any phase changes? So by phase change, I mean light comes in here, it hits the surface, it's reflected. You know, maybe it's coming in like this, but when it's reflected, it's like that. So that would be 180 degrees phase change. Now you get that when you go from a lower to a higher index of refraction. So light would come in here, maybe looking like this, but reflected like that. So it's undergone 180 degrees phase shift. So we've got to put all of this information together. Also, when light is reflected from this interface, it may or may not undergo a phase change. If the index of refraction of N2 is bigger than N1, you also get a phase change. So you may have one here, you may have one here. If you have a phase change here and a phase change here, well, that could possibly work in our favor, because now you've got two phase changes and they cancel each other out. So if you take all that information and put it together, I've made this chart. So the first thing to determine is, well, do you have constructive or destructive interference? If you're actually seeing it up here, it's constructive interference. If you have something like you're trying to get rid of the light for whatever reason, then it's destructive interference. Like an anti-reflective coating would be destructive interference. So the first thing to determine is to take into account all these ideas about phase change. So this refers to looking at N1, N of the film. Let me write it over here. This column here. I'm talking about N1, N of the film, and N2. Now, is the index of refraction of the film the middle value? It's literally in the middle, that's not what I mean. Is it the middle value? So in this example, this is just air, That's 1. This is the film. That's 1.25. This is water down here. This is 1.33. So it's the middle value, right? It's greater than this, but it's less than that. It's the middle value. Okay, so if it's the middle, taking into account those 3 indices of refraction, if it's the middle value, it's greater than one of them but less than the other one, we use this row. So for constructive interference, 2t, and t is the thickness, is a multiple of the wavelength of the film. Okay, so that will give us constructive interference. And m, there's different multiples. M is equal to 1 would be the smallest, give you the smallest thickness of the film. Now for destructive interference, you want the path length to be a half of a multiple of the wavelength, and then you can get destructive interference. We don't have that for this one. Now if it's the largest or the smallest, I'm talking about the index of refraction of the film, is it the largest or smallest of these 3? So is the index of refraction of the film larger than all of these or the smallest of all of these? Then you would use this row to determine what formula to use. So for us, for this problem, it's the middle value. Now if it's the smallest or largest, then like for example, maybe this one's 1.25 and this one is 1. Then it would be the smallest of the 3, and then you would use this row. So it definitely helps to have a little chart like this. The book has a similar chart. It just says something like, are there 1 or 2 or no phase changes? This is already built into my table that I have here. Another thing to remember is this is the index, this is the wavelength of the light in the film. So in our example, they gave you the light outside, 500 nanometers. That was the light not in the film. So to use this formula, you have to use the wavelength in the film. So take the wavelength that's not in the film and then figure out what it is in the film. Okay, so lots of background information for this one. We've determined it's the middle value. We've determined that we're looking at it, so we're seeing it. It's constructive interference. So for this problem, 2t, t is the thickness, and they say the minimum thickness, so that means the minimum thickness would be m is equal to 1 times the wavelength in the film. So we've got 2t, wavelength in the film is the wavelength outside the film, divided by the index of refraction of the film. So you can't see it. There we go. So 2t, minimum thickness, m is equal to 1, wavelength in the film. But the wavelength in the film is the wavelength outside divided by the index of refraction. So then t turns out to be this wavelength to index of refraction of the film. Okay, so minimum thickness m is equal to 1. Now if you have any multiple of that, like if m was equal to 2, it would be twice as thick. M is equal to 3, 3 times as thick as we're finding here. But this is the minimum thickness for this to happen. Okay, so we've got 500 nanometers divided by 2 times index of refraction of the film was 1.25. So it looks like 500 nanometers divided by 2.5. Okay, and this will actually come out in nanometers, which is what they wanted it to be in the formula anyway. Okay, it looks like maybe 200 or so nanometers. You'll have to verify that, but it looks like that's going to be good. Okay, so that's for constructive interference because we actually see it. Let's look at the next one. So the previous problem said strong reflection, meaning that you're seeing it. This one has an anti-reflective coating, so you're trying not to see it. So anti-reflective coatings can be used on the inner surfaces of eyeglasses to reduce the reflection of stray light into the eye, thus reducing eye strain. So maybe you even have something like this. A 90 nanometer thick coating, so that's the thickness, that's T in the formula. Be careful, nanometers, no problem. What must the coating's index of refraction, what must be the coating's index of refraction to be most effective at 480 nanometers? Okay, and assume that the coating's index of refraction is less than that of the lens. Okay, excellent. And then the second part, if the index of refraction of the coating is 1.38, what thickness should the coating be to be most effective at 480? Okay, so let's write this all down. It's really similar to the last one. It's just now we have destructive interference because we're trying to kill off the reflective ray. Okay. Okay, so they give you the thickness, 90 nanometers. We want to have destructive interference for this wavelength of light. So I'm assuming this is just air. So it's kind of similar to what we had before. Here's the film on top of a substance, the substance being the lens, and they're telling us that the index of refraction of the lens down here is just bigger than the index of refraction of the film. So again, the way to do this is to refer to your table. We want destructive interference, and it looks like this is the middle value again. This is going to be bigger than air, but it's going to be less than whatever substance we're on here, probably a lens. So same idea, this is the middle value. Bigger than air, but smaller than whatever it's on. Let's look at the chart here. So it's the middle value again. So for destructive interference, we have 2t is m plus a half times the wavelength in the film. And in this case, they told us it's the minimum thickness, so we're assuming m is equal to 0 because that's as small as this expression can be then. All right, let's use that formula. So 2t m plus a half wavelength in the film. Okay, so m is equal to 0 gives us this. 2t is wavelength in the film over 2. And I'm trying to figure out the index of refraction of the film. So this would be wavelength outside the film, don't forget the 2, and then index of refraction of the film. Okay, so let me just recap. The 2t is still here. When m is equal to 0, this goes away, and we got wavelength in the film divided by 2. Now the wavelength in the film is equal to the wavelength outside the film divided by the index of refraction of the film. So I've taken that and I've plugged it in here for the wavelength of the film. Okay, we'll have to put it all together here in just a second. Let me just clean it up a little bit. That's what we have. So 2t wavelength in the air divided by 2 index of refraction of the film. And that's what we're trying to figure out. So let me put this over here and put the 2t over there. So index of refraction in the film, wavelength outside divided by 4 times t. Let's make sure we did that okay. So this goes over here. The 2t comes down to the bottom, making that 4t. The units all look good. Now if you use the wavelength in nanometers, this is going to come out in nanometers. I can't remember what they actually want the answer is. Okay, so that's for the first part. Now the second part is kind of reverse engineering what we just did. Now if the index of refraction is 1.38, so they're changing it. What if this is 1.38, same 480 nanometers, what is the thickness? Same thing, just kind of do the problem in reverse, referring back to this equation. For m is equal to 0, what would the thickness have to be if the wavelength in the film is found from using 1.38 as the index of refraction? So I'll leave part B to you. It's essentially using this formula, but knowing the index of refraction of the film is 1.38, what would t have to be? Okay, excellent. Let's look at the next one. Okay, just a couple more to go here. For a demonstration, a professor uses a razor blade to cut a thin slit in a piece of aluminum foil. When she shines a laser pointer, a wavelength of 680 nanometers, through the slit onto a screen 5.5 meters away, a diffraction pattern appears. The bright band in the center is 8.2 centimeters wide. and we want to know what is the width of the slit. So this is diffraction. In a sense, it's a wave interfering with itself. If you try to squeeze a wave through a small hole, it breaks into individual parts, and those individual parts interfere with each other. So double slit and diffraction grating is interference patterns. This is called diffraction. It's similar but not exactly the same. And we want the answer here in micrometers. So refer to this section. So from chapter 17, we're just doing 17.1 through 17.5. So let's take a look at what the pattern actually looks like. So if you have a single slit like this, you get a big central maximum and then individual bands spaced apart. Okay, so a few things are the same, but a few things are different. Now, in reference to a double slit, this picture is different. You get a big central maximum. In the double slit picture, there's a central maximum, but it's not twice as big as the other ones. So this is a central maximum. It's twice as big. Okay, so the distance to the screen is the same. It's called L. The slit width is called A, and then we have a wavelength of light coming through. So you have to keep that picture in mind when you're thinking about these different scenarios. Okay, so for a single slit, the formulas that we have, the physics part of it is this. So A is the slit width. So slit size, slit width, whatever you want to call it. Now, for the single slit, the formula gives you where the dark spots are. For the double slit, it was the middle of the bright spots. This is for the dark spots. So instead of calling it M, we're calling it P. It's just an index again. So when P is equal to 1, that gives you one of the spots on either side. Let me show you the picture of that again. Actually, this is a different picture, but this works out very well. So you've got the central maximum right in the center here. So when P is equal to 1, that would give you that dark spot. P is equal to 2 gives you that dark spot. So the central maximum is twice as wide as the distance between, say, 1 and 2. The distance between 1 here and 1 over here is twice as big. Okay, and you get the same kind of pattern over here. So the formula I was just talking about gives you the location of the dark fringes. And the central maximum is twice as big as the separation between any of these other dark spots here. Okay, back to the problem. So again, this is the location of the dark spots. That's the wavelength. Now in the small angle approximation, which probably most of these problems would be, the sine of theta is approximately equal to just theta. So this formula reduces to this formula here. Now purely from the trigonometry again, the tangent of theta is y over L. Like that idea is similar to what we did before, just purely from the trigonometry. Now again, in the small angle approximation, the sine of theta is about equal to the tangent of theta. So if you set the sine of theta equal to the tangent of theta, you get this. So when you're reading through the chapter, wondering where it's coming from, well, the sine of theta is about equal to the tangent of theta. And again, just keep in mind what all these things mean. L is still the distance to the screen, P is just an index, lambda is the wavelength, and A is the slit size. So again, when you read through the chapter, you'll get this for the location of the dark fringes. All I've done for this formula is take y sub p, multiply both sides by L. Now the central maximum is W. It's twice as big as any of the other locations. So if I put 1 in here for y, that would be the distance from the middle over to the first dark spot. Now it's twice as big, though, to get the whole central maximum. So the width of the central maximum is twice this. So if you put p is equal to 1 in here, multiply the whole thing by 2, this will give you the width of the central maximum. So again, for this whole section, definitely have a picture. Let's see how we could apply that to this specific problem. Okay, so this was again the professor cut a slit in a piece of foil, got a diffraction pattern. The pattern's 5.5 meters away. The width of the central maximum is 0.082 meters. How wide is the actual slit? So looks like we could use this formula to figure out what the slit size is, because we know the width given in the problem, we know the wavelength 680 nanometers, and we know the length 5.5 meters. So you have to do a little bit of algebra for this formula. Just solve for A. Looks like A is equal to 2 wavelength L over the slit, the central maximum size rather. Okay, and be careful, I think they want the answer in micrometers. So I guess when I put it into this formula, I would put this as 680 to the minus 9th meters. Put that in for the wavelength. Put this in for the length, 5.5 meters. Do the width is 0.082 meters. The answer is going to come out in meters. You'll have to change it into micrometers. Now, if you're in scientific notation, it'll probably already come out to times 10 to the minus 6th, I would imagine. But anyway, just keep that in mind. All right, let's look at the last problem. Okay, so quality control systems have been developed to remotely measure the diameter of wires using diffraction. A wire with a stated diameter of 170 micrometers, so 170 to the minus 6th, blocks the beam of a 633 nanometer laser, producing a diffraction pattern on a screen 50 centimeters away. The width of the central maximum is 3.77 millimeters. What is the diameter of the wire? Okay, so a wire is stated to have this diameter. Using this diffraction pattern, we're going to try to calculate it and see what it is. So there's a nice example in this section of the book. Let me see if I'm here actually. Yeah. So if you ever want to measure the size of small things, you could use a diffraction pattern to do that on certain items. I don't know if I see it here actually. Yeah, this one. Using diffraction to measure the width of a hair. So it turns out that this hair acts as a single slit. So if you shine light through with the laser pointer, for example, on a single hair, which we could have actually done this in class if we were meeting, if you shine a laser light right through a single hair and you're like a meter away from a wall, you'll actually see the single slit pattern appear. So a hair works just like a single slit. Okay, so this is the wavelength, this is the distance away. Here is W, the width of the central maximum. So this is a way of actually determining the size of things that are small. And you could literally do this if you have a laser pointer. You could do this at your house and a ruler. So that's what's going on in this problem. We have a laser. We know the wavelength of the laser. Here's the distance to the screen. Here's the width of the central maximum. When it says what is the diameter of the wire, what you're trying to figure out is the size of the slit, because the wire is acting just like a slit. So take the single slit formula, and knowing that this is the wavelength of the light, just be careful, put it into meters. This is big L, the distance to the screen. Again, put that in meters. The central maximum, W, 3.77 to the minus 3rd meters. Take all that into the central maximum formula and solve for A. That's the slit width, and that's the size of the wire in this case. So when you get that, compare it to 170 micrometers and see whether or not it's within 1% of the stated value. So laser light with this wavelength, you could measure things that are really small. Things that are even smaller, you might have to use things like X-rays or something like that to measure really, really small things, because that would actually produce a diffraction pattern as well. Really small things, if you can make the wavelength of the light small, you could measure the size of really small things. Okay, any questions, let me know, and I'll talk to you soon. Bye-bye.